This is Unit 13, Nuclear Chemistry. Lesson 1, Radioactive Decay. How is radioactive decay described? The objectives of this lesson: I can identify the type of nuclear decay mode. I can construct nuclear equations for alpha, beta, and positron decay. I can determine the penetrating power of each emission. Do now. So, quick review: isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons, and therefore they have a different mass. So, for example, hydrogen 1 has one proton and therefore one mass. Deuterium has one proton and one neutron, therefore it has two mass. Tritium has one proton and two neutrons, therefore it has a three mass. So these are all isotopes. They're all hydrogen, but they have different masses because they have different numbers of neutrons. Recall atomic notation. We write the symbol of the element here. That top number is the mass of the number, which is the protons plus the neutrons, and the bottom number is the number of protons, which is the atomic number. To get the number of neutrons, you subtract the atomic number from the mass number. Isotopes, again, are the same element, so they have the same number of protons, but different numbers of neutrons. Now, quick review. What is the charge of the nucleus of an oxygen atom? So yes, if you recall, in the nucleus, we have protons and neutrons. So in the nucleus, so our nucleons equal the protons plus the neutrons. If our protons have a positive charge and our neutrons have no charge, the charge of the nucleus is equivalent to the number of protons. So in oxygen, we have 8 protons, therefore we have a positive 8 charge in our nucleus. Radioactive decay is, in simplest terms, an unstable or radioactive nucleus of an atom breaks apart into smaller parts. We call this transmutation. This occurs when the unstable element decays into a new element. It always turns into a more stable element. The stability of the nuclei have to do with a couple of different things. Large atoms are elements with an atomic number greater than 83 are naturally unstable. They're too big. And small atoms are unstable when the atom's mass is not its typical mass on the periodic table. So, for example, carbon is typically 12. So if we have a carbon 13 or a carbon 14, they're typically unstable because that's not our typical mass. And this has to do with the attractive nuclear force pulling our protons and our neutrons together, and then the repulsive force by those positives. All these positive charges repel each other. Therefore, they don't like to stick together. So that's why we have to have a balance of protons and neutrons. If we get an unstable atom, then we release either beta particles, alpha particles, or gamma radiation. And those are our 3 types of radioactive decay. Radioactivity is due to the proton-neutron ratio. So this band of stability refers to the atoms that are stable due to a stable proton-neutron ratio. And this ratio is not 1-to-1. So this is a 1-to-1 neutron radius, proton-to-neutron ratio. And we see that our atoms are stable within a band that is slightly higher, where they have a little bit more neutrons compared to the protons. So table O has the different types of decay, or the different radiation types. In this chart, the number on the upper left is the mass, and the number on the lower left is the charge. So keep that in mind. So for example, here I've got a +1 charge, and up here in helium, the bottom refers to a +2 charge in my nucleus. Natural transmutation is when nuclei of unstable atoms emit radiation, which is from table O, naturally and form a new substance. So remember, don't break the law. We have the laws of conservation of mass and charge. In a nuclear reaction, the mass and the charge must be conserved. So that's basically what we'll be working with. Table N describes the decay modes for selected nuclides. So that's another way to say isotope or nucleo. Right. So the different types of radioactivity. Beta decay are atoms above the belt, and they have too many neutrons, and thus they will have beta decay. The beta particle is an electron created when a neutron decays. So when I look at this formula here, if I have an iodine 131, it undergoes beta decay, and when I undergo beta decay, I release an electron, and therefore I have basically lost a proton, or gained a proton. So now I have a new element. So, for example, thorium 234 undergoes beta decay. So, the total mass on the left must equal the total mass on the right. So, this 234 must equal 0 plus 234. So, those numbers are equal. The total charge on the left must equal the total charge on the right. So, this 90 has to equal 91 plus negative 1. So if I have beta decay, I know one of my products is going to be this beta particle, and the other one I can figure out based on the total mass equaling the left and the right, and the total charge equal on the left and the right. So for example, construct the nuclear equation for carbon 14. Remember that mass and charge must be conserved. So the first thing you'll do is you'll write your isotope symbol. Carbon 14 has a mass of 14, and it will have 6 protons. Now we have to look on table N. So if we look here on table N, we have beta decay, beta minus decay. On table O, we're going to match up the symbol here. Here is my beta negative particle. So we know when carbon 14 decays, one of the particles will be that beta particle. And to figure out what's left over, I need to have my top number, 14, equals 0 plus 14. And my bottom number has to equal 6 plus, well, equal 6. So I have to have a 7. 7 plus a negative 1 is a 6. 7 is no longer carbon. 7 is now nitrogen. So my new element is nitrogen 14. Radioactivity of the positron emission is very similar. This is when I have atoms below the belt of stability and they have too many protons, and they will release basically the opposite of a beta particle. It's an electron with a positive charge, which is a very strange thing, but that's what happens. So the same rules apply. I have to have my mass on the top equal both things, and then the charge on the bottom. So the 6 has to equal my 5 plus my 1. So for example, potassium 37 undergoes positron decay. So the total mass numbers on the left must equal the total mass numbers on the right, 0 plus 37. And the total charge on the left, 19, must equal the total charge on the right, 1 plus 18. So that's how I get a new element, because I'm changing my proton number. So for example, construct the nuclear decay equation for calcium 37. So the first step is you'll write the symbol for calcium, the mass on the top, and the number of protons for calcium is 20. We know calcium undergoes beta plus or positron decay because on table N it tells you that for calcium 37. Over on table O, we find the positron here is beta plus. So that means one of these symbols has to be our product. So when calcium undergoes positron decay, one of the products will be that positron. My mass has to equal, so 37 plus 0 is going to equal 37, and my charges had to equal. So 19 plus 1 equals 20. 19 is no longer calcium, it's now potassium. So we have our transmutation because we have a new element. Radioactivity for alpha decay, atoms with 82 or more protons undergo alpha decay. They have too many protons and neutrons. Alpha particles are weak due to their mass, and alpha particles are the same thing as the helium nuclei. So essentially, that's why we write helium here. That's the symbol. The helium nuclei has 2 protons, so it has a plus 2 charge, and then 2 neutrons, so it has a 4 mass. So uranium-238 undergoes alpha decay. So I have alpha particle as one of my products. The mass on the top has to equal the mass on the top, so 234 plus 4, and the charge on the bottom has to equal the charge on the bottom. So for example, I just did that. And plutonium-239. So remember, the mass and charge must be conserved. So plutonium is Pu. So you'll find that on your reference table if you didn't know it off the top of your head. Plutonium is Pu. All right. So you're going to look on table N to find what type of decay plutonium-239 undergoes. So 239 undergoes alpha decay. It looks like that's like a little fishy. So the little fishy is over here. and that means I have 4 over 2 helium as one of my products. Now I have to find plutonium. What is its, how many protons does plutonium have? So you have to look for plutonium. It's number 94. So 94 is our bottom number. So we know that 239 is going to equal to 4 plus whatever equals 239. So 235 plus 4 will equal 239. And then I know that 94 has to equal 2 plus 92. So 92 is no longer plutonium, 92 is uranium. So this is my new element. So my mass and my charges are conserved. Now, gamma decay is the strongest particle. It accompanies most decay, and it's usually not written due to the fact that it cannot change the mass or charge of any of the species. Our gamma particle has no mass and no charge. It's just energy. And this is the most damaging because it's just energy and we can't see it. So the penetrating power of alpha rays, beta rays, and gamma rays varies greatly. Alpha particles can be blocked by a few pieces of paper because they have a large mass. Beta particles can pass through paper but will be stopped by aluminum foil. So here's our beta particle, the dotted line. And then gamma rays are the most difficult to stop and require concrete or lead or other heavy shielding to block them. And that has to do with no mass. So if I have a large mass, I have less penetrating power. So on table O, the alpha particle has the least penetrating power, the very top one, because it has the largest mass. Least penetrating, largest mass. And then the most penetrating is that gamma radiation because it has no mass. So it can go through anything. So radiation is also charged, and it can be separated by a magnetic field. So alpha particles, because they have a positive charge, will be drawn towards the negative plate. If I had a magnetic plate, gamma particles will go right through because they have no charge, and then beta particles, because they have a negative charge, will be attracted to that positive. So opposites attract. All right, so check your understanding. And now you can identify the type of nuclear decay mode. You can construct nuclear equations for alpha, beta, and positron decay, and you can determine the penetrating power of each emission.